Thank you. So thank you everybody for being here and for having me. I'm going to introduce to you what I have been researching for now 20 years, even though the connection with quantum physics came a bit later. Just so you know, I could give an entire semester course about this, and of course I have to condense everything to half an hour, so of course I'm not going to be complete. But what I tried to do is to make it in such a way that it fits in maybe 30, 35 minutes and that we have time for questions. So I'm just going to scratch the surface and try to give you something concrete like visuals and so on. And then I will give you pointers. There's a whole website that I started to try to explain to a broad audience how it works. And of course, all the published papers that you can look at. All right, so what I'm doing is basically trying to contribute a local realist extension of quantum theory, but of course there's a trick, and the trick is to touch free choice, so to adapt the free choice assumption. And so the way that we're doing this is by interpreting quantum experiments as games between observers and the universe. And I like to use the visuals with what I saw in Richard Feynman's lectures, with these devices that you can basically summarize quantum experiments as choosing a setting, like a measurement basis, and then you push the corresponding button, and then you have a light bulb that switches on and off if the outcome is just one of two possibilities. And so the idea is that the person who presses the button, that's the observer, the experimenter, for example, and then the light bulb, instead of being probabilistic, it's action by the universe that we will represent with the cat, Alfred, right here, who makes the decision on whether the light bulb is going to switch on or not, right? So this is on the high level the idea. So I'm turning quantum theory into not a probabilistic theory, but a decision theory. So what I'm going to start with, because I'm assuming you're not all familiar with game theory, so I'm going to give a very high level impression of game theory so that I'm able to explain the model to you. So the idea is that in game theory, if you take it from a 30,000 feet perspective, you basically have two kinds of games. You have the games that are in normal form, and you can think, since you're physicists, about it as space-like separation. You have people in different rooms not communicating with each other. And then you can model the game as a matrix where one player picks a row and the other player picks a column. And then once they have made their choices independently, you get rewards or payoffs. The first reward is for the row player, Alice, and the second reward in every cell is for the column player, right? So, and then there's a whole field, that's what game theory is about, to decide what people should do. So this is the first kind of game, right? So normal form. The other kind of game is in extensive form. You can think of it like chess. You play in turns, so you're informed about the previous moves, and then it's something dynamic. And so this we represent with a tree structure. This is also called extensive form, and you can also think of it as time-like separation. Where I'm connecting it to special relativity will become clear hopefully later in the talk, right? So these are the two kinds of games. Now, game theory is not just about these games, it's also about defining concepts and reasonings and algorithms that say what should be rational for the people to do. And what we call rational is maximizing the reward. You basically want to maximize your reward, but you have to take into account the opponent's reasoning. And so the most common solution concept in the literature is the Nash equilibrium for this kind of games, right? And the idea is that you optimize, but fixing the opponent's reward. So I have an example here, so you can see. So this here is a Nash equilibrium. And the reason it's a Nash equilibrium is if you consider that Bob here could change their choice between these three columns, then you see that 6 here is higher than these two. So if you freeze Alice's choice, then this is optimal. And the same goes if you freeze Bob's choice and Alice unilaterally deviates, she also maximizes here. So this is the definition of the Nash equilibrium. We say they are best responses to each other. So this is for this kind of games. And then we also have something that turns out to also be a special case of a Nash equilibrium, but it's called the subgame perfect equilibrium, which is based on a backwards induction. You basically start at the leaves and then work your way back. In fact, when you play chess, this is what you do, right? Of course, we don't have the computing power to actually solve chess, but technically, we would do it with a backward induction, starting from the future and working our way back to the past, right? So this is mainstream, this is classical game theory, and free choice, I'll come back to it, is basically this idea that you deviate unilaterally, which is this same notion of independence when you make a free choice. So this is the connection between quantum physics, or at least impossibility theorems, and game theory. It's this unilateral deviation where you freeze the opponent's strategy and then move just over a row or just over a column. So that was the very quick high-level intro to game theory. Of course, also that can be covered in an entire semester's worth of mathematical formulations and theorems, but this is basically the idea. So now I'm coming to how with this kind of games, we can model quantum experiments. So the idea is that we have Alice, she's an observer, we have Bob, he's an observer, we have Alfred, who is the universe, and we have this equipment. But we'll have plenty of copies of this equipment at various places, space-like separated or even time-like separated. In fact, I have in mind the, who knows the process matrix framework? Quite a few of you, okay. So this is exactly the idea, but with fixed causal order. I'm not interested in indefinite causal order or anything like that. Everything is a fixed causal order. So I basically can view it as a DAG, as a dependency graph that represents the experiments. But basically, the idea is that every time you have a quantum scenario, quantum experiment that can be modeled with a process matrix with fixed causal order, then you can also convert it to a game like this. So I'm going to show you plenty of examples. I think it's the best way to proceed. So this is an example where I just have one single measurement lab, right, with Alice. She can press one of two buttons and the universe answers with either the light bulb on or off, and that gives 4 possibilities, right? So every time I use what could be considered random variables, or I think you call them SV, space-time variables, also in papers in this group. So A, X, and Y. But really, you know, a random variable is just a function from the omega space to a target set, right? So this is why I still call them random variables, even though there's no, we don't need probabilities. But basically, this is the idea. So Alice, this is the semantics of a tree. You start at the top. Alice can pick between a measurement X, just X alone, or Y alone. And then if she picks X, then the universe can pick between light bulb on or off. Here's something more complex. That's an adaptive measurement. So the idea is that in that case, in the case that Alice measures, presses button Y and gets 0, then Bob can, at that point, press in the future another button on some other device, either W or Z, and get an answer for either one, right? So this is an adaptive measurement. This actually goes a bit further than the process matrix framework, because the process matrix framework, you don't have adaptive, right? All the settings can be specified in advance in the conditional part of the probabilities, but we can do adaptive measurements in this way. Now you can even have, you know, more complicated things, like in that case, in every single possibility out of Alice's lab, 4 of them, you can do something different in Bob's lab, right? So that's just as an example. All right. What comes next is what if you want to test locality, right? So instead of being one after each other, Alice is here, Bob is there, and they're space-like separated, so very far away, they do not communicate. For now, I'm assuming Alice has just one button and Bob has one button. I'll put 2 buttons a bit later for the EPR experiment, but just for the sake of explaining. So on one lab, Alice presses X and gets 0 or 1, Bob presses Z and gets 0 or 1. But there's a problem with this in terms of game theory, that that's not a tree. So it's not the normal form. It's also not the extensive form. What do we do about it? Well, it turns out that there is a way to do some sort of unification of the two. If you take a step back and realize there's space-like separation, time-like separation, so you can generalize it to something, to a bigger game structure that I call space-time game, which looks like this, consisting of directly acyclic graphs. But it turns out you can turn it back to a tree, which is actually great news for using the algorithms of game theory. And the way you do that is you take what's called a linearization of that causal order, right? So the only constraint is A must be before X, B must be before Z. If you just apply this constraint, there are 6 possibilities of the orders that you can get between these 4 variables. Who agrees? Right? These are all the ways you can order these 4 variables respecting the constraints of the causal order. This is one of them. So in that case, I took A, B, X, Z, right? So this would be if you put them in this order. You know, since you're physicists, I can use this analogy. In special relativity, you know that with space-like separation, the order of the events depends on the observer, right? When it's time-like separated, everybody agrees, but when it's space-like separated, they might not agree. So this is why, because they are space-like separated, we get this margin of freedom here. So this is, if you take that linearization, you can convert it to a game like this. And there is something new here. It's the dashed line here that connects these two, because there is basically, if for a given observer, X comes before Z, then that observer will see that choice be made before that other choice. But in fact, because it's space-like separated, the cat right here doesn't know what the decision is made here because they're space-like separated. That's exactly what these dashed lines actually means. It's that you don't know if you're here or if you're here. So we connect them. In game theory, that's called imperfect information. It means that when you make the decision here, you are not informed if you are here or if you are here. So you basically don't know if the light bulb on the other side went on or off. So there's the first interesting connection between physics and game theory here. It is that imperfect information in game theory can be interpreted in terms of locality from a physical perspective because they are space-like separated. And this is the reason why there is this dashed line. So that's the first connection. You can also make a connection between these 2 forms. So that's a space-like, the space-time game. This outcome right here corresponds to 0, 0. So that would be this. The second one to 0 and 1. So you see the second light bulb switches to 1. Then this combination right here, 1, 0, gives you this. And here you have 1, 1. That gives you this, right? So you see in the space-time form, you have combinatorics. It's a combination of some of the nodes. But when you convert it to a tree, every leaf in the tree gives you exactly 1 possible history, right? You take any leaf and then you read back the path that gives you all the settings and measurements that actually happen in the world corresponding to the leaf in the game. So far, so good? Okay. So just for the sake of completeness, if we pick a different observer, the order might be different, right? For example, we might have AXBZ, ABZX, BAXZ, BXZ, BAZX. But there's very good news, and that's actually something that worked incredibly well. It turns out that these games that you see on the right are all equivalent, also in game theory. There is somebody called Thompson who defined what's called the Thompson transformation between these trees here. They're all equivalent. That's great because it means it's Lorentz invariant, if I simplify a little bit. It means that we don't care which one of the orders we take here, constrained by the causal dependencies. It doesn't matter. All the games are the same. So we can pick arbitrarily one of these and work on it. All right. Next, these dashed lines are actually even more interesting than just for locality. It turns out that they can also be used in conjunction with the non-contextuality. So this is another game that here corresponds to, I think, what's called a 3 cycle in non-contextuality. It basically means you have 3 choices of settings that you can take, and you take 2 among 3. So either X and Y, or X and Z, or Y and Z. So that gives you here, these are no longer singletons. Now there's sets of 2 elements. These are called the contexts, right? So the context label the edges. And then depending on the context, you activate decisions by the cat. So if you have X, Y, these 2 are going to be activated, right? So these 2 are going to give you a result. If you pick X, Z, then X and Z will be activated. But you notice the dashed line here that's connecting the 2 axes here. They basically say it's the same thing. So this is in essence, non-contextuality, right? So the choosing the outcome of measurement X is the same thing, regardless of whether it's measured with Y or Z. So you can also represent this as a space-time game that looks like just like this. So it's not just locality, it's also more broadly capable of modeling non-contextuality. Now, this was a space-time game, right? But you can also convert it in extensive form. There's an algorithm that does that I published. So you still have the three contexts, you still have decisions, but now it's a tree. So you can look at any one of these leaves right here, corresponds to exactly one possible history that this can take. Right. Are you still with me? Right. Okay. And now, just to show you, we can also do logical AND and OR. So AND would be when you connect a node with two constraints on its input. So here it means that this measurement is only taking place if X was performed and leads to 1, and Z was performed and leads to 0. If the two of them holds, then that activates this decision right here. So that's a logical AND. And for the logical OR, you can connect with dashed lines all of these nodes here. So that would be the previous case without the dashed lines where it was adaptive. But if you all connect with dashed lines, you basically make it exogenous. So it means that in that case, the choice of setting that Bob picks is fully exogenous and is decided can be decided in advance, right? So that would be in the spirit of the process matrix framework. All right. So this is the kind of the menu of the sort of things you can do with these games models, the space-time games. So you can basically model any quantum scenario with labs in any fixed causal order, so any DAG of labs, and build a game like this. But now let's go further than that and take the Bell experiment. So it means we have two labs, so 2 to 2, right? So two agents, two settings, and two outcomes per settings. This is what we get when we model this as a game. So Alice has a choice. Let's say, I think classically you take 0 or pi over 2 for a spin for Alice, and pi over 4 or 3 pi over 4 for Bob. And on the other side, it's not a tree, not a problem. We apply the algorithm. This is what we get. We get again a tree. And you can verify that each one of the leaves here, that is right here, corresponds to one possible history that the experiment can go. So the one marked in green, for example, means that Alex picked X, Bob picked Z, and then on Alice's side, the light bulb did not switch on, for example, spin up, and then on the other side, spin down. All right. So this would be the modeling of the EPR experiment as a game. So you see, it's already slightly more complex in the extensive form representation, but it works. You can actually do that. Now, what's interesting is when you start looking at strategies in the sense of game theory. So when you have a game like this, you can actually consider the master plans that the people can have. So for example, there is a master plan of Alice. It's not very complicated in that case. It's just like which button she intends to push. Bob also can have a master plan between the two settings that he can pick. And then there is the universe's master plan with that would contain, it's basically, as I will explain, a hidden variable model. It basically is a choice for X, for Y, for W, or for Z picked in advance. And basically, picking deterministically a strategy means picking a row here. So the one marked in green means the universe intends to answer 0 for X, 0 for Y, 1 for W, 1 for Z. And when you put it all together, Alice's choice of setting, Bob's choice of setting, and the universe, you get what's marked in green is here, where Y and W are ignored, and you only read X equals 0 and Z equals 1. Right? So that would be a deterministic version. That's what in game theory we call a pure strategy. Right? Who is with me? Right. Okay. Now, when it gets interesting is when you start repeating the experiment many times and looking at frequencies, because this is where we reach the Bell inequalities case. So imagine that now we run the game a million times, and we just gather, like a Galton plank, right? We just gather the frequencies for each leaf of the game, so the number of times that it's going to be to happen, and we get these frequencies here, right? I just generated some random numbers here very rapidly, but just for the sake of exemplifying the distribution. All right, so we now look at repeated experiments. Now, where the connection with game theory is very interesting is that in game theory, there is something we call a mixed strategy. So the difference between a pure strategy and a mixed strategy is that in a pure strategy, you pick one specific assignment, right? One master plan. But in a mixed strategy, you instead pick a probability distribution over them. For example, here you would decide, as is done commonly in EPR, like 1/2 for the buttons on Alice and Bob's sides. And then you have this probability distribution over all the possible assignments. That is, in fact, a deterministic hidden variable model. When you put it all together, you get this some distribution over all the possible histories. So that's actually this. That's what you get here. And what's very interesting is that if you look closer, because, for example, if Alice picks X and B picks W, only the values of X and W are relevant. And what happens is that, in fact, you take the marginal probability, right? You sum over all the other variables. So, in fact, what you get here is 1/4 of the marginal probability for XW, XZ, YW, and YZ. Everybody with me? Right. So the magic is that then that connects with sheaf cohomology and the question of, can you have a global section? If for example, I give you a specific frequency distribution, and I ask the question, can you find a probability distribution on all 4 variables so that the marginal probabilities would give you this, right? So this is also called the global section. We are looking for a global section. Who is familiar with these things? I assume not so many. Okay, so so forget about sheaf cohomology. So the question we ask is basically, can we find a joint distribution that would give us these marginal probabilities right here? As it turns out, we have impossibility theorems. And the idea is that because of what I explained, that imperfect information is tied to locality and non-contextuality, the strategic form can be seen as a form of realism, right? If you look here, that's a form of realism that you would in advance define the outcome of the measurements that you are doing. So that corresponds to realism. And then I told you at the beginning of my talk that measurement independence corresponds to unilateral deviations, right? This free choice, the fact that the setting is exogenous. But the thing is, if you actually do this connection, what you observe when you do the computation of the frequency distribution for all possible histories, you get exactly this. And this is in fact exactly the same causal model that you have in Bell inequalities when you factor them out. So they factor in this way. And because we find exactly this same causal dependencies, the same causal model, what that gives us is that we have free choice, we have local realism, and as a consequence, there is a Bell inequality that constrains what we can get. So it means that the moment you do it like this, you take mixed strategies and so on, meaning a joint probability distribution, and you obtain frequencies like that, the Bell inequality is going to tell you that if you sum up the purple cells here, so the purple probability numbers, you have to get something that is larger than 1/4. I picked it from a paper by Roger Kolbeck that was presented 7 years ago here at ETH, which is basically the CHSH inequality, but visually it's just about summing these 8 numbers. So basically what you can conclude is that if the sum of these 8 numbers is greater than 1/4, then you could possibly find the joint probability distribution and explain it with a deterministic hidden variable model. But if it's below 1/4, then you know you can't. And that would be, in the case, the EPR experiments with carefully picked settings and outcomes that break this inequality. So you can say with certainty here that you will not be able to find any joint probability distribution. In other words, you will not find a deterministic hidden variable model. But what that tells us, because these are all known physics all known results in physics, is that if you connect it to game theory, it means that this cannot be used for describing quantum theory. The way that Nash game theory works with the mixed strategies is constrained by Bell inequalities. So we know it doesn't work, and we need something different from Nash game theory in order to be able to break the Bell inequalities. All right? But there is good news. It's because we know that Nash doesn't work, but I have been working for now 20 years about an alternate form of game theory that I call non-Nashian game theory. And the difference between non-Nashian game theory and Nash game theory is free choice. It's the fact that in Nash game theory, we assume that decisions are independent. But in non-Nashian game theory, we assume that you can predict future decisions, and there might be counterfactual dependencies or dependencies more generally between the various decisions. So I like to compare it to the switch to non-Euclidean geometry, right? You have the Euclidean postulate that seems obvious. When you have a parallel line and a point, you can only draw one parallel line through the point in Euclidean geometry. But it turns out you can change that and you get hyperbolic geometry, Riemannian geometry, and so on. The same happens in game theory. If you change the assumption that the decisions are independent from each other and replace it with an assumption that the decisions can be perfectly predicted in advance, then you get non-Nashian game theory, and it turns out to be consistent. So what we do is the trick to basically break the Bell inequality is that instead of the free choice and unilateral deviation, we basically assume that we know in advance what the result will be, the prediction of an individual run, but we find the only one that is immune to that. That is basically a fixed point. So there are papers out there that give you the algorithm. So I'm not going to give everything. I'm just going to give you an example. But basically, you can refer to these three papers to find all of the algorithms for any kind of game, normal form, extensive form, or the space-time form. The algorithms are all in there. So let me just directly show you on one example. So this is the game I showed you at the beginning, right? You might remember. This is the Nash equilibrium, right? Because we have here that 5 is bigger than 2 and 4, and 6 is bigger than 5 and 0, right? So if you consider unilateral deviations, we are stuck here. But even in game theory, people agree that this is a problem. Because if you look at this other possibility here, that would give something higher for both players. Right? So we kind of have a dilemma here. Like we are stuck in there with the Nash equilibrium, even though everybody knows that AB would be better. It turns out that non-Nashian game theory solves that. So now I'm going to give you the resolution, the non-Nashian resolution of that game. What's really nice about it is that I typically explain it to my friends on a napkin over dinner. So you don't need to know the theory and so on. You can read the papers if you want, but I can really just explain it directly at the level of a high school student or even a junior high school student who would solve the game for non-Nashian resolution. So the idea is this. We are looking for fixed points in the sense that the solution has to be known in advance and still reached by both players. So can this be the solution, 4-4? Can it be known in advance? And in fact, if you look closer, it's absurd. It's absurd because imagine that Alice would know that in advance, that she would get 4. But Alice also knows that if she picks Z, no matter what happens, she gets at least 5, right? Z guarantees her 5. So do you agree it would be absurd that this would be the future and Alice would see the future and know in advance that the result is going to be a reward of 4, but then she would have not acted rationally because she could have gotten at least 5 with Z. So this is absurd. It's reductio ad absurdum. So we delete that solution. And to do it more systematically, what we actually do algorithmically is that on every possibility of Alice, we look at the worst case. So here the worst case is 1, here the worst case is 0, and here the worst case is 5. And then we look at the maximum of these worst cases. That's called the maximum, the maximum of the minimums. So here 5 is the max, so we keep the 5, and everything that is below 5 gets discarded. It's just not possible. It's logically impossible. It is not immune to knowing in advance that this would be the solution. So we just get rid of them. Then we do the same thing for Bob. So if you look at Bob, here the worst case is 0, here the worst case is 2, and here the worst case is 3. And then you look at the maximum worst case, 0, 2, and 3, so that's 3. and then you delete as absurd anything that gives below 3 to Bob, because he would have played you if he had known. So then you combine and you get rid of plenty of results here, and then you just iterate. It's just a recursion, like you do it over and over and over and over and over again. So if you do it again here, then you basically notice that, here, there is a guarantee of 8 for Bob to play S. Here, the worst case would be 5, 6. So that's 8, that is the maximum in that case. And we delete these 2. So what we've done is eliminated everything that doesn't make sense, everything that is absurd, we just get rid of it until at the end, one possibility remains, right? 2 things can happen. Either 1 remains and you're done, or 0 remains. You've basically proven that so many are impossible that they are all impossible. That is also a possibility. In that case, there is no solution. But it is going to be 0 or 1, right? But never more than 1 in any case. The only assumption is what's called general position. We don't have equal payoffs. These are all different numbers in the table. All right, so that's the unique solution. And hopefully now, if I give you any game, you should be able to reproduce exactly the same technique of just eliminating the absurd and finding the solution. Okay, and so the idea of the non-Nashian thinking is that you deviate in diagonal, meaning that Alice could basically say, if I had picked Z, so the solution is X, but if I had picked Z, Bob would have picked U. And this is where you see that it's no longer free choice, the sense that it is commonly assumed, because we assume that there is a counterfactual dependency between the choice of Alice and Bob. Okay. So yes, that was basically the non-Nashian resolution. Now I'm going to show you visuals and not the details, so only focus on the visuals, because this is just to give you an impression. The idea is that this game here, I told you that the space-time games generalize it, can be represented as this game in this form as well, right? There's a choice between 3 possibilities for Alice and 3 for Bob, right? So I could use this game. I could turn it into the extensive form, and you see there's exactly the same rewards here. There's 9 of them, just like the 9 of them here. It's just a different form. And then I can apply my algorithm on that game. I'm going to find the same result. So I just start at the top, and then I eliminate what is impossible, and I'm going to find the same solution, right? So you can look at the papers for more details, but it's consistent and gives you the same solution. Now, what's interesting is that, as I will show you, it corresponds to a forward induction, which is more natural than the backward induction in chess. But the best way to show you that is to give you a visual. And again, just focus on the visual that I'm going to show you, not the details of the reasoning. We basically start at the top, on the origin of time, so at the very beginning, and look at the decisions that are taken no matter what, right? So Alice and Bob, anyway, pick a setting. Then I apply my iteration of deletion, deletion, deletion. I look for everything that is not possible, anything that is inconsistent, and I delete it, right, as logically impossible. And then I continue, and I delete. Now what's interesting is that one decision now is known, right? I have eliminated so much that all the Y side of Alice goes away. So I know that Alice is not going to pick Y. That tells us that this decision here of the cat for the axis X, because we know Alice picks X, the decision of X is going to happen too, so it activates. Then I can continue, and so on. So what's very interesting is that you see the elapse of time here. The reasoning here is done exactly in the same direction as the arrow of time, which is very intuitive compared to the backward induction, right? So in that case, we arrive to this. And so now if you remember that this models a quantum experiment, this basically means that this algorithm tells you that Alice picks X and finds the result 1, Bob picks W and finds the result 0, right? It's a deterministic prediction. I like to compare the resolution mechanism with this quote. How often have I said to you that when you have eliminated the impossible, whatever remains, however improbable, must be the truth, that you might know by Sherlock Holmes. So this is really the core of the algorithm. I'm almost done. So this is the website that you can go to if you're interested. So with many more details. I just wanted to tell you, like Florian here with us is a master's student who is writing his master's thesis. And what we're trying to do now is to instantiate that model into a theory. And what is missing in the model is the rewards to put there. The structure we know, that we know how to build from the process matrix, but we don't know yet the formulas that we should put in there. So we are trying to use AI. Florian is trying to use AI to derive them from the expected probabilities with the Born rule. And it turns out that it actually seems to be working quite well. So this is in case of the EPR experiments, that's called the loss landscape in machine learning. And you see that we do find some optimal solutions in there. So this is ongoing, but it looks so far very promising in terms of being able to instantiate the rewards in a way that gives us the Born rule. So I think I can already stop here for questions if you have any, and discuss a little bit. So again, it's just a very high level overview, but I hope that it's provided an introduction for you.